You. Oh. And you can speak.
No, that's really
Okay.
so. The IETF attendance is quite significantly down actually this meeting. But it's a good turnout, unless people were staying for the cultural video and they just decided to stay here. Good afternoon, everybody. Welcome to the SDN Research Group. We have quite a tight agenda, so I think we can start. So just a reminder that you are being recorded and you are implicitly subscribing to the IETF and the IRTF IPR policy, so please make sure that you pay attention to the note well, and if you disagree, then again you should probably leave. So for today, you will find our Sdnrg wiki and charter, something actually we may talk about at the end of the session. We've got our mailing list, essentially all of the proceedings, so the meeting materials will be available later on. You can participate remotely. We already have a number of people in the Jabber room. Currently, I'm logged into Jabber, but did we have a volunteer to be an additional Jabber scribe? Yeah, thanks, Drew. Okay, 4 minutes just to capture the questions, sort of the salient points, any particular actions. We have Will, our recently appointed secretary. So thank you, Will. It'll be great if we have someone to support Will. Hand me on. Yep. Okay, great. So we've got 2-minute takers. Excellent. Okay, so it's the housekeeping. So on the agenda today, we're going to start off with a recap of one of our working group documents. This is Cooperating Layered Architectures for SDN. It's a document that we adopted in the research group approximately 2 IETFs ago, I think. So now we need to kind of work on that, make some progress, and hopefully move that forwards to publication. Then the second part of the session will be one of our special topics. This is sort of network telemetry in the domain of SDN and also big data analytics. So there's kind of the aspect there of collecting information and data, sort of monitoring, using it for root cause analysis or sort of network optimization or resource optimization, but also using SDN infrastructure to deliver big data applications. So we have a number of sort of architecture discussions, big picture, kind of grand research challenges, and then a couple of presentations on tools, protocols that might be applicable, certainly available. And then towards the end of the session, we're going to revert back to sort of general SDN topics, kind of eclectic mix of subjects, some of which we've already seen before: ACTN, abstraction control of the transport network. This is an activity that's occurred in the IETF, in the TEAS working group, and we're going to get an update, find out the latest information in terms of interoperability and where the protocol work and the data modeling and information models, how they've progressed. We've also got a topic on SDN security, again, sort of a fairly interesting set of challenges that we've seen already, perhaps with SDN and to a certain degree NFV, in terms of trust models, threat vectors. So we've got an update there across a number of topics associated with security in SDN and some NFV. And then if we still have some time, hopefully we've got some time available at the end of the meeting to just kind of review the state of the SDN research group itself. I did sort of attempt to start a discussion on the list a couple of months ago, kind of failed, you know, so maybe this is an opportunity to come to the mic, kind of talk about what works, what doesn't work within the SDN research group. It's very important that sort of this opportunity, the forum to talk about SDN grand challenges reflects, what you potentially researchers, whether it's academic or industrial researchers, are working on. Where can we kind of collaborate? Can we identify some of the issues? Can we work together to solve them? And in these slides, we also talk about some other modes of operation, whether it's trying to co-locate the SDN research group between IETF meetings. Maybe we can look at co-locating with one of the more academic orientated events, again related to SDN, or maybe something that's more industrial focused. Some of you may have attended Layer 123 a few weeks ago in The Hague, where EWSDN was co-located, and that seemed to be quite a successful venture. Cool. So are there any objections to the agenda? Would anyone like to introduce any other topics? No, going once, twice, okay, 3 times. So can we have our first speaker, please? Is there a clicker? Oh, yeah. Okay. I think you need a USB. That's all. Sorry, we have an incompatibility issue with the USB. Can you just make sure that the USB click works? Yeah, great.
So, hi everybody, my name is Carlos Bernardos from University Carlos III Madrid, and I'm presenting this on behalf of my co-authors. Closer to the mic. Now better? Okay. So I was saying that I'm Carlos. I'm presenting on behalf of my co-authors, Luis and Diego from Telefónica, Mohamed from Orange, and Paula from Ericsson. So a bit of a recap from about what the draft is about. Well, the draft is about a new architecture proposition on splitting the scope of SDN. So we have a clear responsibility boundaries between the transport, the connectivity side of that, and the service, because current architecture may go into a bit more monolithic approach, and that has or poses different weaknesses or disadvantages as the ones that are listed in the slide. Monolithic control architecture, making more difficult to reuse components, having no clear boundaries on what is every module doing, these kind of things that we wanted to basically address in this proposal. So I'm not going to go into, spend more time on this because this has been presented already in past meetings. Then a bit of history of the document. As Daniel mentioned, this was adopted some IETF meetings ago, and basically we have been working on different comments that we have received. Unfortunately, we were not able to address all the comments in the version that we submitted for this IETF, but we are working on those, as we will go through later in the presentation. And basically what, the main changes so far from the previous version was about changing a bit the terminology. We are moving from transport to connectivity, as it better reflects what we mean by the transport part of the architecture. And we also added some references to the SDIF 005 document on the use of SDN for NFV, which is one of the use cases that we include in the document. So the next steps, which is basically the main topic for this presentation, is on addressing the comments that we received. We have a very good list of comments, as we will go through later, that are still pending to be included in the version that we are currently working on but couldn't really submit. So we want to go through, well, basically remind that we are working on those and ask for any other people that may want to provide comments to do so, because our goal is to submit a new version, including all these comments plus the additional ones that you may have before the end of the year. So the idea is to be ready for potential publication of the documents by the next IETF. So that's basically the goal. So just a few words on this use case, just to basically reflect what we are doing with this SDN architecture. We have here that if we see the NFV architecture, I think you are all familiar with this. We have two different responsibilities or two different areas where SDN can be applied. One is on the NFVI infrastructure and the NFVI, where we basically the SDN control may be used to interconnect the different BNFs at the NFVI level, or also to connect with the PNFs, with the physical network functions. That's one level. That will be basically the transport, the connectivity layer that we refer in the document. And then we have also that the SDN can be used at the service level. So we can use that to configure the different BNFs, so at the service level. So this two-layer approach is what basically we describe in the document. And this is the use case. And actually this figure is included in this SDNFV EF 005 document where Luis and Diego, for example, contributed. So, comments. I mentioned that we have quite a lot of comments, very good comments that we received in the past. Here these are listed. So we have comments from editorial things that we will fix, to also including or referring to existing work being done in other parts of IETF, like CCAM working group. We have some clarification that needs to be added. We have also some suggestion of addressing in more detail multi-domain scenarios. We have some comments on existing work at an FVRG document. So all these comments will be addressed in the version that we are currently working on. And the idea is basically to see if you have any additional comments. And as I mentioned, we commit to provide a new version by the end of the year. And we hope that will be ready for publication before the next IETF, or to discuss that in the next IETF in Chicago. So any additional comments, questions?
Will from Huawei. Could you please go back to the slides of NFV? Yeah, this applicable. I didn't see the figure in your draft. Have you updated?
In the draft, it's not yet there. We will put it there. Yeah, we only added text in the figure. I mean, in the draft, in the section of the NFV use case, but we will add the picture. We just add basically the reference to the document, but we will add the figure. Yes, okay. For clarification purposes. Yes.
So thank you. Good luck with the ASCII art for inserting the figure in the document. So there was a lot of support on the list for the document. You know,
yeah.
we tended to sort of be quite hesitant about making sort of adopting in the research group a particular piece of work. But we thought that this document was very important to help with maintaining consistency around definition of sort of layers, relationships, interfaces, etc., especially between some of the IETF working groups such as TEAS, CCAMP, etc. I think it's really important to make sure that the people that originally supported the document also help now with the contribution, and making sure that when the new revision has been submitted and it's available, that you actually go through the document and ensure that whichever comment or sort of discussion point you had has been adequately addressed. You know, and just a response to the authors to say yes or yay or nay. And if it's nay, then you make sure that you sort of go out of your way to help. If it's even better, actually provide text. So we really want to kind of develop the document into something that we can kind of use. And the cooperation, the layered architecture within sort of an SDN is potentially a very important topic that can be discussed in the context of some of the open source projects. We've got things like OpenO, a variety of, so Open Orchestrator and a variety of SDN controllers. It may be worth kind of thinking about, you know, how this kind of framework, how these architectures and layers can be applied to some of those efforts. So there's a question at the mic.
Yeah. Parviz Yagani, Huawei. I was actually curious to know why the other mapping options from the ETSI EVE 005 were not really considered as part of this proposal or this draft.
Well, this is because that mapping option is the one that basically comes from this work, from this architectural proposition of this separation. So that's why basically we are mentioning this proposal is being considered at Sdnrg as one of the approaches. So it's not, it's just, I mean, there are other options, but the one that we are considering this one, and that's being reflected there.
So this is an example, it's not baseline.
Yeah, it's an example, yes.
So there are like 3 more options.
Yeah. Sure. Okay. Any other comments? Okay, so just to your point of getting feedback from the original people that provided comments, we plan to, once we have the update, to basically, in addition to send that to the main list, to basically ask point to point to the guys that provided comments to ensure that we capture correctly those comments.
Cool, thanks. So we're now entering the second part of the session, which was our special topic, specifically SDN, or network telemetry, sort of big data infrastructure, analytics in the context of software-defined networks. When we issued the CFP, we were looking at sort of all aspects, potentially, of network telemetry and big data. And we've got a few interesting presentations now. Just wondering if we should keep questions to the end of the special session, so we kind of have a sort of an interactive discussion. It would be really good if we can get people to the mic again to kind of pose questions based on sort of what the presenters have highlighted. Also, if you have a particular research project or a theme of research that you're working on, then you feel free to come up to the mic and kind of state that and let us know what you're working on. Even better though, follow up on the list. You know, let's really try to kind of make these special sessions sort of useful, especially, and continue the discussion beyond, you know, these IETF sessions at the IETF. Cool. So if we can have our first speaker for the big data network telemetry discussion. Network health assessment. So Chin, are you here yet? I know Chin's already contacted me. He mentioned that he had an overlap with the Lime working group, which is running concurrently. They moved him to the front of the session. I guess he's not finished. So apologies for that. He should be here shortly. Let's move on to the second presentation. Moritz. Yep. And we've tried to allow 15 minutes, 15 to 20 minutes per presentation, with plenty of time for questions. I know in the past we've had kind of a situation where we've been running quite hot, and we haven't always had the chance to kind of address all of the questions at the mic. So we're going to try and leave plenty of room this session for questions. Thank you, Moritz.
Okay, hi, my name is Moritz Müller. I work for SIDN, which is the registry of .NL. And thank you. We have roughly 5.6 million domain names registered, so they create a bunch of traffic at our name service, and we had the challenge to store this data and also to analyze this data. So we had a few requirements. We want to store it efficiently in a way that we don't spend too much storage for the traffic. We want to query it efficiently to get results within a few minutes or seconds. We want to test large number of hypotheses on our data, and finally also continuously keep adding new data. And we looked at different kind of solutions. So we could convert the PCAP file into text-based file formats like CSV, for example, and run Hadoop MapReduce jobs on them. Or we can just store them in relational databases or no SQL databases. But with most options, we had the challenges that it was quite hard to scale and they didn't deliver the performance that we wanted to. So we basically built our own platform based on open source components of the Hadoop framework, which is Impala as a query engine, Parquet as a file format for storage, and the distributed file system HDFS. What we're currently doing is we store the traffic of 4 of our 8 name servers on the cluster, which consists mostly of TCP/IP traffic or TCP/IP information, of course, DNS queries and response data, and we also store ICMP traffic. This is relatively DNS specific, but I think we can extend that quite easily to other protocols as well, and it's open source, you can try and check it out. Yeah. So this is roughly the architecture that we have here. So the white parts are basically the open source components we already we had there. So we have different nodes. In our case, we have 6 different nodes. On each node that spans the distributed file system HDFS, which includes data replication, which means that we have a data block which gets replicated across 3 different nodes, which gives us redundancy. So if one node fails, we can still access the data, and we can also run queries in parallel. Then we use the Parquet file format to store the data there, and the Parquet file format has the advantage that it is quite good to compress the data and also quite easy to get the data from the file system again. And above all, there runs Impala, which is the query engine, which supports an SQL-like format, so we can just put in the queries in an SQL-like statement, and we get the data back. Another advantage of Impala is that it basically handles the queries on its own, so we don't have to think about how we spread the queries across different nodes. Impala takes care of it. Basically, yeah. The part on the right, which is the dark gray stuff, is the things we developed. So we have kind of a workflow where every 10 minutes we get the data from our name servers as PCAP data. Then we run the converter, and where we merge the DNS responses, we merge the DNS queries, we add some additional information, for example, about the location of the resolvers. We take some information away that we don't need. We extract some metrics that we publish with Graphite and Grafana to get some more information about how the cluster is running, and now actually get some additional information already about the DNS traffic. And then we store the data in Parquet files, which is then written into the Hadoop cluster. So I mentioned before, we are TLD registered. We run this platform for 2 years, a bit more 2 years now, and we are quite happy with the results. And we have now over 150 billion rows of DNS query and response data stored there, which is roughly 21 terabytes of data in Parquet files, so not in PCAP files. We also have a bunch of use cases because storing is only one thing. We also want to extract the information and to have some additional value. The goal of this platform was basically to increase the security and stability of .NL, of the zone, which is kind of generic, but we have a few use cases that try to tackle that. We extract some statistics. These statistics are mainly for operational purposes, so we get some more insight about what kind of queries we get. It's kind of similar to DSC, but you can dive a bit more into detail about what we're queried for example, and where the queries come from. We also publish this data on our website. We do some scientific research with it as well. We create support for our operators. So for example, we give them some insight in what happens when we change the publication of the zone file from 2 hours to every 1 hour. And of course, also when we get, for example, a DDoS attack, or we are misused in a DDoS attack, and then we can also get some more insight from where this stuff came from. Then we have 2 also more security-related use cases, which is malicious domain detection and botnet infection detection, and I want to explain them a bit in more detail. So the malicious domain detection is kind of based on the assumption or on the observation that domain names which are registered for malicious purposes usually have a different query pattern in DNS than domain names that are benign, that are usually good domain names. And This is also the observation we did, but also many other researchers have had this observation already. And here on the left side, you can see the number of queries for domain names which are newly registered and which are good. And you see a very slow growth in queries. That's query per day, so it's not very much. And on the opposite, on the right side, you see the number of queries for phishing domain names, for example. And you see that these domain names get a lot of queries on the first day already, and then after a few days it goes down because maybe the domain name was blocked or the phishing campaign is over. So what we're doing is we get every single day the newly registered domain names. We get the characteristics of these domain names from our data platform, which is the number of queries that we get for this domain name, the number of unique sources that we see for this domain name. Then we run a simple k-means clustering algorithm on it, and this gives us then two clusters, with one cluster which we consider as harmless domain names and one cluster that we consider as suspicious domain names. Because we can't really verify very often the suspicion, because some domain names might hide the fish on some URL very far behind, we share this information with a few of our registrars. That's a prototype right now, and they can then verify our suspicion and then take actions based on it, so they can suspend the domain name, for example. A second use case is based on botnet infection detection. So in this case, it's the detection of a very specific botnet, which has clients that are used for the distribution of spamming mails, and these clients have implemented their own resolver, which is interesting because usually we don't see traffic directly from the clients because they usually are behind a recursive resolver. But in this case, they query us directly if they want to spam .nl domain names. And this resolver has some weird behavior. For example, it has a very limited range of ports that it uses and a very limited range of query IDs. And based on these characteristics, we can detect these domain names, these infected clients. We are quite confident about the detection rate, so we have a quite high accuracy there. And so we share this information with Dutch registries, Dutch ISPs, and they can also then take actions based on that, and they can take they can inform, for example, the customer that, hey, you have an infected client in your network, do something about that. This botnet was more or less active in the beginning of and the end of last year, but it varies a lot. So sometimes we see more infections, and sometimes we see less. But it's a very old botnet, but still it's kind of active. And we also see that the activity across the planet is tending more towards the east, but we also see quite a lot of infections in Italy for some reason. So as a summary, we have developed this data platform to get more insights into our network traffic. This is, however, very specific for DNS right now, but maybe this gives you an idea how you can collect a lot of network traffic and apply it to your use case. It's open source, so you can download it, and of course, we're happy if you also contribute to it. Right now, I think 5 or 6 registries are using it or testing it, so we have a slowly growing user base. And that's basically it. I'm not sure if you do questions now or...
So any questions? So I have a question. How applicable would the platform have been to the recent attack on Dyn?
It's applicable in that case as long as you get the traffic to your name service, it's fine. But probably because you have some other cleaning services before your network, before your authoritative name service, you will never see this traffic at your name service, and then we won't see this data in the platform as well. So this is a problem.
Okay.
Yeah, I have a question. My name is Naiming Shen from Cisco Systems. Yeah, just have a question on the botnet detection portion. Is this just for history, or there is a way to use this data to help us to detect the future botnets?
No, it is kind of reactive. So
Okay.
the botnet has to be active, and then we see the infections.
Okay, thank you.
So, well, thank you for the presentation. I mean, one thing we're sort of trying to encourage is to use the SDN research group as a place to kind of state some challenges, maybe that you might see with your architecture. Maybe there is some primitive of SDN that you think might be applicable to the platform, or there's perhaps some kind of forwarding technology In this case with DNS, it's not immediately obvious, but feel free to use the list
All right.
as you continue to build and develop the platform. But thank you. Good. Okay. So has Chin arrived from the Lime working group? Doesn't look like it. So okay, let's have our next speaker, which will be Heyu. Apologies if I haven't pronounced your name correctly. You can. Okay.
Good afternoon, everyone. This is Heyu Song from Huawei Technologies. Today, I'm going to talk about dynamic network probes on smart data plane. So, has anybody heard about those terms, POP, P4, PIF? If so, congratulations, you are at the front line of the next generation of smart data plane. We call that smart data plane because it's programmable, and this programmability is open to the third parties and the network operators. So this kind of data plane can support custom forwarding functions. Also, it supports programmable in-network computing. This can not only shorten the time to market of your product, also it enable novel applications you cannot imagine today. So what's composed of a smart data plane? Basically, there are two parts. The first part is a programmable data path chip, which might be NPU, CPU, FPGA, and emerging flexible ASICs. Also, it includes the server-grade local control processor with enhanced CPU, memory, storage, and also the interface to the forwarding chip with higher bandwidth. Also, in a scale-out architecture, we can also support, dedicated clusters, even dedicated servers, and even server clusters to function as a local processor. So the right side figure just show you the possible smart data plane in SDN architecture. First, we need to clarify several concepts. Configurable versus programmable. So configurability means the functions has already hard-coded in either software or hardware into the data plane devices. You may have some knobs to tune its parameters, or you have some switches to turn on or turn off some function blocks, right? But the bottom line is that every function is already there. You cannot add any new stuff in it if it doesn't exist at the design time. So that means also the hardware, the resources are all pre-allocated. You don't have a freedom to save some resource from one purpose to other purpose. But for the programmability, which means the data plane device is empty at first. You have nothing in it. All the functions your forwarding process can be downloaded at the runtime or before the runtime. So, which means it supports on-demand resource allocation. You can just allocate enough resource for your application exactly as is needed, no more, no less. Also, if you want some new functions to be added, you can do that. Just to replace the old design with the new one. So, but we can even do better. If we just do this static programming, which means we have some function running in the data plane. Later, we want to replace it. We have to compile another program and download it to the data plane. Even it just consists of a very tiny modification. So this causes a service interruption and maybe a long deployment latency. So the idea is we can support interactive programming, which means the on-demand and real-time modification to the data plane devices. If we want to some minor modification, we just download the new function blocks to replace the old one. So this can support runtime function and feature update and support many interesting interactive applications. So why we want to do this? So mainly we want to address service providers' pain point is that the lack of real-time and full visibility of their networks. But we believe SDN provide a unique vantage point to the network service providers in that SDN controller can oversee the entire network. So we believe the network visibility will be a key application for SDN. And also this network visibility can be considered a big data problem. That's because we need standards to collect data, encapsulate data, and present the data to the applications. Also, we want to make the data plane to play a more important role rather than simply functioning as a raw data source, which means we need to dig data plane potential for better data collection and pre-processing. Also, this data source needs to cover the entire infrastructure from end to end. Also, not only the data processing, but also the traffic management, also including the physical interface and the switch fabric everywhere. But also, this network data analytics must be dynamic, which means we cannot foresee at design time what data we need to collect. So because we don't understand how the application will use this data plane as a data source. So everything must be on demand and dynamic. So therefore, we design this idea of dynamic network probes. We call that DNP. These probes are essentially just some finite state machine. We have various programmable components in the data plane, such as counters, meters, timestamps, timers, and filters. By composing these components into a probe, we can realize some type of finite state machine. And we can insert this finite state machine at some proper locations to monitor the status or state in the data plane. And once an event is triggered, it can report the event to the controller. Thus, we can avoid the raw data of sending raw data to the data plane. We can save the bandwidth between the controller and the forwarding plane. We can also make the latency much reduced. So so the benefit of the DNP is twofold. First is it's support in-network stateful processing, which means it's a very much bandwidth efficiency for the control and data plane interaction. Also, it supports dynamic resource allocation, which means the data plane resource utilization is very efficient. We can have two different type of programming models to utilize the DNP. The first one is we can provide a standard API layer for the upper layer applications. So this API layer essentially it isolates the application from the actual data plane, and every application's request will be translated to some DNP through this API layer. This can isolate malicious attacks from the application. Also, it's good for the data plane to understand where and when to insert this DNPs and when the data should be fed back to the application. So we already find that SQL-like API is feasible if we consider the data plane as a streaming database. But there could be other possibilities. So we are looking for that too. The second possible programming model, we call that network map reduce. If you compare the SDN architecture with a map reduce programming model, you'll see the similarity immediately. right? Because data plane is also a distributed system. Each node in networks will see only partial of the streaming network data. So, which means if we can make the SDN controller a job tracker, it can disaggregate some network problems into the map functions and the reduce functions, and you can map the put the map functions in some selected subset of network elements. And once the partial streaming data is processed, the data will be shuffled to another set of network nodes for further reduced processing. And finally, the result will be reported back to the SDN controller. So this is a very elegant architecture. We have shown quite a few network applications, such as DDoS detection can be deployed with such a model. So to verify the feasibility of the DMP, we have a prototype 18 or NE40E based platform. On the front end, we can use a P4 or C language to program our forwarding applications and then download it to our data plane through the POF interface. And after that, we can have other measurement applications to again reuse this POF interface to add the DMPs to the data plane and collect data from it. First, we compare this DMP with the static programming process. We can see if we use static programming, we will need to recompile the application and replace the old one with this new one. It will take about 2 seconds to finish. But if we want to deploy the DMP, it only costs us 50 milliseconds to configure the new DMP to the data plane, which counts for about 40 times improvement on the latency. It's quite good. Also, we know if we deploy this DMP, we do consume some data plane resources. For example, if we simply add a counter to some flow, we want to monitor the flow, so we can keep add new counters to the new flows. By doing this, we will see how scalable the system is. And with our experiments shows we can add almost 14,000 counters to the system without sacrificing the forwarding throughput, which means this solution is quite scalable. So there are some challenges, research challenges. We need to guarantee the system safety, security, and coherency, and the performance. We just list a few challenges here, and there are much more challenges. We want to find more collaborators to work on this to address those challenges. Also, there are also still many missing components on the SDP ecosystem. We are missing language, model, API, and system. We believe all these pieces must be completed to make this system useful. We are also looking for new applications and new use cases on DMP and the smart data plane. Now we already show it's very useful for network analytics and network OEM, but we are certainly looking for more interesting applications. And we also want to find collaborators to promote the trend and the technologies. We believe there are still a significant research and standardization efforts in front of us. There are also some related works in IETF. First one is in-band network telemetry and in-band OEM. Both those two technologies can use a static programming feature. But ours is more dynamic. We can insert, modify the data plane at runtime, which means it's much more flexible. Also, the gRPC provide a framework to retrieve information from the data plane. That's another related work. So our conclusions: We believe that dynamic probe is perfect for network analytics, and it will be a very useful tool. But we are very interested to know how you are going to use the smart data plane, and also how should IETF, IRTF to address these challenges. That's concluded my talk. Thank you.
Thank you, Heyyu. Okay, so questions? No questions. Oh,
Hi, I'm De Kutscher. So it's interesting that you looked into OAM and analysis like as your prime use case for smart data plane. I think, I mean, there's lots of potential, right? I mean, like new protocols, like new forwarding strategies, maybe better interaction between network and transport protocols. These things are, like in theory, not now possible.
Yep.
Is that something you're also looking into, or are you focusing really on the OAM part?
Right now, we believe that's a very important use case. Also, the security, traffic engineering, they all rely on some data collection capabilities. So we can see in my first few slides, I show that there are several categories of possible application scenarios. But the OAM is very important to us. Yeah.
Okay, thanks.
Dan Bogdanovic. All your probes, if I understand correctly, are passive probes, right?
Yeah, first step, we try to avoid any active modification to the folding behavior. So these probes are all passive. They just mean to collect data from data plane. They don't mean to change the folding behavior. Yeah.
No, it was the idea of changing the forwarding behavior, but creating a active probe that would generate some performance measuring traffic. For example, that you would use that to generate the probes to send down, the data plane.
Right. Those packets only involve traffic between the control plane and the data plane. Right. So
no, you could do it across your data plane.
Also, we are possible, generate some new packets and also maybe modify some. For example, we add some timestamp to the existing package. That's possible. But our idea is it shouldn't change the folding behavior to the normal traffic. If the packet forwarded from A to B, we won't change that.
No, I'm saying that you generate a packet that will go from point A to point B, and then measure across, that behavior, how that packet is being forwarded by the data plane.
Right.
Because as you generate a packet and you have the analytics on each node, you can then essentially do certain verifications of your service topologies.
Yeah. You can consider that's part of the active behavior, but the idea is if we have a API layer, we can just isolate the application to avoid any application to do bad things to your data plane, and also we also want to monitor the performance impact to the data plane. If you want to do something that will negatively impact the throughput of your data plane, we should deny the request. There should be something to do to be done to avoid that.
So the API itself from the smart data plane, how do you intend to publish that? Will that be part of an open source project or integrated in part of a control or an application that runs on top? Or?
There are multiple paths. First, one, we believe, an open community, open source efforts might be good to approach that. Actually, we already seen some academic research to approach in that way. Also, I think maybe some standardization organization should also address this, because we believe there's a very big branch of application for the SDN, and it deserves its own efforts on standard.
Okay, cool. Thank you. Has Chin arrived? No. Okay, Robin. Yes, you're up. So we're moving from sort of API from the data plane to network intelligence.
Okay, I think the programming the hardware is also the part of work, network artificial intelligence. Okay, a joke. Okay, this is Robin from Huawei. Yeah, I'm the architect, Sdn, chief architect of the Huawei Sdn controller. Okay, so today I will like to introduce the topic is the architecture of network artificial intelligence. I think this is the new research topic in the Sdn area. I would like to share the opinions to you and to collect your comments. Okay. Okay, this is the introduction. So I think now that the artificial intelligence has is important. Can I take this down? Okay. Okay, I want to advertise like this one because now that artificial intelligence is already a very important technical trends in many fields in industry. For example, we use that I think the famous AlphaGo of this Google to do this artificial intelligence to beat the human that's the component of this the chess or some this other game. And also we have this artificial intelligence for some this proposed to analyze the user's behavior, to understanding their behavior and to predict their the shopping this behavior and to recommend the appropriate commercial items to the users. I think this is very popular in the IT world. But now I think this artificial intelligence and should be also be introduced in the network because for the past years a lot of people talking about the SDN and we talk about the programming. This is the flow table path programming. We talk about the programming hardware. We talk about the fast northbound interface and the south inner bounds. And we talk about the traffic optimization. But I think that all the work together in summary is just to prove the right road to the network artificial intelligence. Because this the controller is just the brain of the network. You should to do more thinking about your the work, do the perception and the cognition of the network. Then you can save the manpower, from the people. Because now that is our IP network is very complex. A lot of carriers complain that our IP network makes them too hard deploy the business and to propose a new service. So now that why we use the SDN, we use some of this automated the application service provisioning like this one. But now that is I think I want to give this level to think about this one. We think this is just a network intelligence, artificial intelligence, and to release the carrier's customer from this the tedious work of maintaining the IP network and make our this IP network smart and intelligent, not complex, not tedious. And this is release the network engineers work because we can have more time to think about the future, think about the more ideas instead always to maintain different network VPNs, different this security measures. I think this is also the work to help ourselves, the network engineers. So I think this is very important. I just give some this the use case. So it's a self adjustment of the network, not is a manual adjustment of the network, and also self optimization of the network instead of this the manual optimize the network. I think now that we propose the PCE plus solution. This is just a typical example of this use case because we use the PSAP and a PCE server to calculate the optimal traffic and this is the solution. Then we use initiate stiff TE that tunnel to set up this tunnel to steer the traffic. So I think this is self-optimization, but maybe this is in the early phase, but this is an important example in the industry. And the third one is self-recovery. Some failure happens, you must recover. But now the use case of the recovery is manual recovery. The people have to locate the possible failures in the network, but because IP network always IGP flooding and also the BGP and is to update this flooding, so that it is hard for the people to understand what failure happens, but it is also hard for the people to recover network from the failure. So I think this can be the self-recovery. So and also now this is a telemetrics work is also is very interesting. I think this, in my opinion, this just means intelligent traffic monitoring. So need to collect more network state, make the brain of the controller more smart, so you can do more work, so that it can help the customer and also help the network engineers. So I think this, for example, this intelligent failure location. And also the next one is the traffic prediction, because based on the traffic, you collect from the network, more network states. The more you collect from network, the more intelligent the controller and the network will become. Okay, so this draft we propose the architecture of network artificial intelligence. So this is we try to define a reference model and the key components and the key protocol extension requirements. Okay. Okay, so this before this one, I like to according to my practice in the past 6 years, I like to identify my observation about and also my thinking on the roadmap of development of the SDN controller. At the beginning, the SDN controller wanted to replace the word, but at the last, I think this is just plus SDN. We have the traditional pass calculation, but now plus SDN, plus some this is the PCE work, so become the smart traffic engineering. That means you can do the self-traffic optimization of the network. We have the traditional deployment, but the deployment is time-consuming and the error prone. Plus SDN, but becomes the instant service, because this automated L3 pin provision and the L2 VPN provision. And the next one, traditional, we have the OEM. The OEM is very complex. Layer 1, layer 2, layer 3, layer 4, layer to the layer 7. Every layer has its OEM mechanism. So that for the network engineer, it's very difficult to locate the failure. So now that plus SDN, maybe we can have the intelligent OEM, so that depend on all kinds of the OEM mechanisms, not the manually, so easy to locate the failure. So I think we call it as the intelligent OEM. So now that is because in the first phase, that is just the first step, that the different scenarios, you have the different application. That is for one controller, one functionality. But now I think the second phase is emerging, that the people that thinks they want to use multiple controller to fulfill the work, because this is the use case from the users. For example, the Vodafone, I propose the use case is seamless MPLS. This is for the multiple controller for the traffic optimization. For the lower layer, that is intra-domain traffic optimization. For the upper layer super controller, we do the end-to-end BGP traffic optimization. In fact, we finished the demo 2 times, so we understand, try to master the hierarchical architecture of the SDN controller. The second use case, because for the data center controller, because we have the large data center, maybe the multi-POS. For each POS, we have the controller, but the multi-POS to that is a controller, and also the data center interconnection, we also have a controller. For these controllers, how to coordinate it, how to orchestrate it, how to control it together, so that to fulfill this the wonderful data center SDN solution. So we think they call this is the SDNI. We call it as a inter-SDN controller. That means the multi-controller to fulfill the work. And also now in the industry, some people call it as a hierarchy controller, and also this is some of the controller federation. But to my point, this we call it the inter-controller. That means no matter the vertical this multiple controller or the horizontal multiple controller, but in our opinion, this is the inter SDN controller. So we think the third step we are thinking, so this is network artificial intelligence, because we have do a lot of work in the past years, but now we think network artificial intelligence we proposed, we found that we still in the early phase of this work, because we understand in the IT industry for the past years, after almost 40 years research in the industry and the practice, until today, they think the network artificial intelligence just to achieve the intelligence of the boy or some of the kids only 3 years old. But for Google or some of this important, this bigger IT guys, the artificial intelligence level is maybe 7 years old. But because for my opinion, though we do a lot of work in the past years, but until today, I think if you think the network artificial intelligence, maybe just not only more than 1 year, because the intelligence level. So I think this need a lot of work to be done. This including the programming, the hardware, including the programming network, need the programming orchestrator, need this is the high performance northbound interface, southbound interface. We need that also the brain need more intelligence, such as intelligent machine learning, and this is the decision tree, and also this is a lot of this the failure patterns. According to this, to implement the objective of the network perception and cognition. So I think this is very important, this one. So here we just propose this, the reference model is here. So we can see here, this is the central controller and also this network device. So this is one. So this one, we propose this 4 components of the reference model. The first one is a central controller. Central controller is a key component of the reference model, because the controller is the brain of the network, is a key role of the network, because all these things should be triggered by the brain, by the SDN controller. So this one. The second one is a network device. Network device, because this is a systematic work. Because if you want to make the brain intelligent, your body, that means if you think your body, think your brain. If your brain want to do smart, and your body must also be strong. Because now that I think if you want to support this intelligence of the brain, now that for the network device, lack of too many mechanisms, so that we need the programming, the hardware. So this is the way. But also we understand for the past years, OEM work is not good enough to support the intelligence. We have a lot of the OEM mechanism, but the basic that IP OEM, because IP in fact is complex, because IP is a load balance and also is a lot of shortest path, best effort. You cannot know the right way of the IP routing path. If you cannot know the routing path, okay, 2 minutes. Okay, so if you cannot know the routing path, so you must cannot to detect the failure of the IP path. So once the failure happens in the IP network, it's hard for the network engineer to get the right location of the failures. Okay, so the third one, I think the southbound protocol and the models of the controller. Because if you want to the intelligence, you need to collect the huge data from the network. But now the performance of the SMP and the netconf cannot satisfy this performance requirement. So we need to introduce more this high performance, the protocols. So I think this is a challenge work. I think this work should be done in IETF. So I think the first one is a northbound interface. Northbound interface that I think this one, because your brain is smart, your body is strong, but you cannot show the details to the end users. You must make end users is simple. So your northbound interface must be simple and be abstract, and make the user is just to send a simple the command to the network brain, so the brain can do the huge work and to feedback to the user. So this can release the network customer and to network engineering from the tedious work and huge work from the IP network. Okay, I think this is the requirement of the protocol extension. I don't want to identify this each pieces, so please refer to my draft. Okay, and this now that we begin to initiate the open source work based on the honors. So this is please visit the wiki page in the honors network artificial intelligence. And here we can give this some typical. This means log search engine and the detection of the abnormal log. So I think this is a typical use case. And here we use we can see some of the open source. So there's machine learning. We have a lot of this one. We borrow from the IT world to this is the machine learning. We use some running code and we use a typical use case to verify this concept, and we move on and this one. So here I like to welcome you to join the open source work and make the future happen. Okay. So the next step, so I think this is my suggestion. So I think now that is because this new era and this new era always overlapped. New brain and the old brain always overlapped. But now I think that we must to determine the right working group or research group to do this work. So this including maybe in the routing area, because I'm the draft is RTG working group. But I think this also advanced topic in the Sdn area. So I think I also presented in the Sdnrg. But also this related with telemetry, because this related operation and management. I think this related with OPS area. And also maybe we need some of this new working group. How to know, but I maybe to get this comments from this the Sdnrg, and tomorrow I will collect this from the RTG working group in the routing area. So I think determine this one. And then this we incorporate this more advanced innovation ideas and into this this draft. And then we will begin to promote the protocol extensions in different area under the network artificial in architecture, because I already proposed the protocol extension requirement. So the next one is collaboratively contribute to the open source on the honors. Okay, so because we are aware of this the hard work and this maybe the huge work in this field. So this one, I think this is the community is set up by the Chinese, this technical guys. So that is here. We maybe do this work in the OpenStack, Open Daylight, or NFV, and this honors and OpenO, and maybe some of this Sdn lab. On the same time, because the different layer, we have this different work. Architecture, that is all the controller and all the controller and the orchestrator will be involved. And also this need the end-to-end solution and the model and the protocol and also this standard and also this the device and orchestrator. So all the work together maybe make this happen. So we need your help so that outcome, because for example, because our is difficult for us to use the WhatsApp, but we set up the WeChat. This is from the Chinese, the Tencent company. And also that is WeChat ID. This is mine. So I welcome you to involved in this work and make the network artificial intelligence happen. Okay, that's all. Thank you.
Okay, so I think we can have one question.
Okay.
One?
Yeah.
Okay. How is this different from goals in the Anima working group?
Sure.
How is this different from the goals in the Anima working group.
Go.
What you listed on your first
Oh, okay. I see.
on what you listed on your first page with the requirements, this read like the goals of the Anima working group.
Yeah, I think the Sdnrg group, I tell you. So I think we have this one. The first one, I think this from I think for the network artificial intelligence is make our the SDN work will be overlapped. Some in the new area, some is in the old area, some is old brain, some is the new brain. So I think in the new brain, so I think we need because for our the network engineers, maybe not the machine learning big data. So I think this work we may do some of the academic research. So I think this should be done in the Sdnrg. And maybe some of this existing work we need enhancement of the BGP or some of the PSAP or some of this the performance of protocol. Maybe we do the routing area and the operation area. So that's this one. So and the most important, I think here I think this is our the Sdners. This is the platform. I hope you can join this work and welcome you join the open source work. Okay, that's all. Thanks.
Thank you, Robin. Eric? Just sorry, Eric, to interject. Where are the blue sheets? Does anyone have the blue sheets? There should be 2 blue sheets. No one has who hasn't signed the blue sheets? Okay. If you can just continue to pass around the blue sheets to make sure we've captured everyone's signature who's still in the room. Thank you, Eric.
IETF 96, there was a presentation about gRPC use cases. This is going to be a little bit more about the middle ground between the protocol, where you see with the current draft that's out, that has all the bits and the bytes, but it's not quite the higher level system or the context. And so it's a little bit below the use cases and a little bit above the protocol. I'm Eric Anderson, I'm from Google. And gRPC itself is a client-server remote procedure call. So it's got functions and messages. It is not object-oriented. It is not a message queue. It is not those sorts of things. It's really more of a functional, or not functional but it's really more of you've got a function, you pass a message, you receive a message. It's open source version of Google's RPC system. It's really more properly the next generation of the Google RPC system. We are using it internally, but we'll be using it more and more and trying to replace the current one. Development is happening on GitHub. Things actually happen first on GitHub, and then we use them internally at Google. Anyone else who's going to come and contribute can do the same thing, and we've got some contributors because of that. There's 3 implementations. There's a C version, not C++, but C, Java, and Go. Those are the cores. Then to satisfy many of the other languages that people like to do things in, those build off of the C version. And to give us sort of a scope of the types of problems that we're really trying to solve, we're really looking at embedded to mobile to server. And embedded here, I'm even talking like microcontrollers. We're not afraid of those. The C implementation does not currently work on a microcontroller platform, but that's because they're each a little bit different, and we don't want to waste our time until someone has one in mind that they want. And then as far as network topologies, we're looking at within the data center, which is where a lot of us are, and that's a little easier. Mobile to cloud, cloud to cloud, and device to device, which really encompasses basically everything. So there should really be very few niche places that gRPC we aren't targeting, and those would be highly niche. So about myself, I'm the Java tech lead, and in relation to the draft, I work with Abhishek and Louis and JSP Manager, and whenever I joined the team, there was already some protocol. I've worked through some of the protocol changes that we've done, and so I should be fine if y'all have any questions about it. And I've got a little bit more of HTTP background and look a lot of the HTTP2 stuff. So to bring things up a little bit, This is protobuf IDL as sort of an example. There's a service. It has say hello is just the method on it, and it receives a request and it returns a response. Not very special. This is protobuf. gRPC itself doesn't care about whether you like protocol buffers or we've got some flat buffer and thrift support that are sort of there. If you like some other marshaller, go for it. We're not too upset about that. But most of the interesting stuff is really going to be within the requests and responses. We try to get out of the way pretty quickly. One thing that you may have noticed was not on the previous slide is an exception or anything like that. There is a canonical response status, which has a canonical set of codes and a textual message for debugging. Those canonical codes are specific to gRPC, or they're gRPC defined. They're not HTTP status codes, and that they can be looked up, but those are sort of helpful. And then we support cancellation propagation and deadline propagation. Deadlines can be, you can inform the server what your deadline is so that it can handle that appropriately. And then several other runtimes support linking an incoming request to outgoing requests. So if a server needs to do some more RPCs in order to satisfy an RPC, those can all be linked up. So if the topmost RPC of sort of a fan-out tree is canceled or its deadline is exceeded, that can propagate all the way through all the children. That varies some based on language, though. And now we get, so that's sort of more a little bit standard RPC. I mean, it's different around the edges, but streaming, though, is something that's very unique. Don't see it very often. Basically, I said before, you've got a request and you've got a response. Streaming, though, is 0 to many requests and 0 many to responses. It's bidirectional full duplex. It's flow controlled. It's going to be in order, and it's going to be best effort. It sounds a lot like TCP, but it's going to be for messages instead. And this is really, really useful whenever you want notification systems or things like that. You can have an RPC to open up a request for, I'm interested in notifications of certain types. Then you can start receiving them. You don't have to do any long polling and then reestablishing the poll once you get a response and things like that. And so streaming is not something that you need every day, but whenever you need it now and you want it. And today, you're sort of left with going and rolling your own thing and sort of not being served. And it can also be a natural scoping mechanism for if you've got a bunch of contextual items, the client and server can both keep some state associated with the stream. If one of them goes away or something happens, the stream won't be killed. They can clean up their state, and so it won't be leaked. And so going back to the example a little bit, this is what it was, and we just add in a streaming keyword, and then we get streaming. And so now those are 0 to many. You can just put streaming on client side, you can just put streaming on server side, or which one gets to do the streaming, or you can have both. And then going a little bit further, we've got a metadata concept, which is a sort of side channel. It's the primary extension mechanism for things that are not specific to a particular service. So auth would be a great example for this, or tracing, distributed tracing. You can extend the messages, or you can extend with metadata what is being sent and include authentication information, for example. It can also be useful for if something goes wrong, you can provide very detailed error information that's application specific, because the status is generic and predefined. And then there's other sorts of things like TLS mutual auth and message compression. And then here's sort of the sort of flow. We've got metadata headers, which at the very beginning, a message is sort of half close. Then the server can respond with headers, message, and some trailing metadata with a status. Note that unary, in this case, we've got a single request, we've got a single response. The streaming case is, or the unary is just a special case of streaming. On the wire, they're the same, and then it's just sort of a simplification for users who are doing the simple thing. So simplification for the generated code that we do. So that's sort of the higher level semantics and things, but how does that start diving into the actual draft that's out? The RPC method turns into a path, an HTTP path of service name / method name, and we use post here. The metadata is going to be headers and trailers. Those are HTTP headers and trailers, and messages are going to be linked prefixed frames within the HTTP body. So this should not be very seem very interesting in many ways, but just with that, we're able to do a lot of things on top of that. I think a main difference is having linked prefixed messages is pretty uncommon because most people don't do streaming. But with this, we can do reverse proxying, which is important because we really want to be able to work from mobile to cloud and all these other use cases. And you need to be able to support intermediaries. If you're doing simpler things where you're only point to point, it's not a big of a deal. So through all this, we're only using HTTP 1.1 semantics, but we're using some features that are commonly not handled or implemented or pushed as far as we're pushing them. And so that one thing is trailers. Trailers are commonly not used. We definitely use them because we need to know at the very end of a streaming RPC that how it was successful or not, what the failure code was, and those sorts of things. And then we're also we want concurrent requests and responses, so you can have your nice bidirectional full duplex streaming. That's permitted by HTTP 1.1, but not everyone does that. And then also cancellation is there; it's possible. It's not necessarily as refined in many implementations. But our implementations are not built on HTTP 1; they're built on HTTP 2. It's multiplexing on, you can multiplex multiple RPCs all on the same connection, and that substantially reduces the cost of security for TLS specifically. And that's very, very important whenever you're talking about all the different use cases that we're talking about. Because you're now having multiple connections all on one, you've got to reintroduce a couple of things that TCP might do, like flow control. We convert normal byte-based flow control into message-based so that people don't quite have to worry about the bytes. And you also need to worry about making sure that things go away nicely and clean up without spurious errors. Even though HTTP2 might look like a longer spec than you might be used to, it's actually fine for low resource usage. It's not that big of a deal. And then we've got all the things sort of on top that we can build that are not part of the protocol, but things of part of it being part of a system and implementation. So messages, we're okay with kilobytes. That's completely fine. If you want to do hundreds of megabytes, that's fine too. No big deal. We'd probably suggest doing smaller, but it's up to you. Pluggable name discovery. Not everyone uses DNS. There's plenty of other things out there, and we support anything that you would want to do, adding that in plugin. Client-side load balancing is another thing. You want sort of smart clients at times where they can automatically cycle through multiple connections or do round robin or things like that. And then reflection, and then there's also some conversion to REST abilities for that subset of clients who just don't want to use gRPC, and you want to provide them with a sort of more classic mechanism for communication. And that was the talk. You can contact me, and there's some related things you might be interested in here. This gets into more of outside of my scope and more into y'all's.
So thank you, Eric. We've got time for just one question.
So this is Sonal from Cisco Systems. So I had a question. Can you have messages that are interdependent with each other, or are they completely independent messages?
Sort of in a streaming case? Or?
Yeah.
Yes. So the full bidirectional full duplex means that you can see one request, respond to it in a reply, and then see another request and respond to it in a reply. So you can do I mean, so the analogous situation with TCP, you can do those sorts of things in TCP. I think that that's a good model to sort of mental model for the stream. So yes, when we totally do that, that's part of the point.
Okay.
Great.
And
And
also,
sorry, can we take the question to the list? Because I lied, there was 2 questions, because I have a question myself. gRPC was mentioned in the context of the smart data plane presentation earlier. So, clearly from the kind of characteristics of the protocol and the messaging, it's highly applicable to sort of OAM, network telemetry. Can you give us any examples of where gRPC is used? Is there any open source available?
I don't think that those. So there's the network management thing that I just posted there. That's, I think, pretty new. I think some of the other examples aren't open source. There's definitely things that do that, but you might be able to see more in the future.
Okay, cool, thanks. Chin, do we see you? Yeah, great. So we're going to sort of go back in time to our first presentation, which was Chin talking about network health assessments. So Chin, thank you for coming, and just as punishment for being slightly late, we're going to have to reduce your presentation time.
Okay. Okay, good afternoon, everyone. Sorry for my late, actually, for conflict meeting. And my topic is about network health assessment using big data and to perform the network diagnosis and predict. Close the microphone. Okay. Yeah. Thank you. Next. So as we know, actually, troubleshooting is very hard, and for many different reasons, given the scale of the network, variety of service, and customer high expectation for the service quality and anticipated network change, network events. So sometimes network problem is caused by the misconfiguration, maybe protocol bugs and load balancing issue, long latency, and maybe packet loss. In some cases, actually, when the network gets down, actually, it's hard to know when you can recover from it. So this is something we really want to dig into and try to leverage this big data technology and to achieve a very short service recovery time. So the agenda I want to talk about first, what is network health assessment, and then we will lay out the architecture overview, and we will give several use cases, and then we will talk about several key components we look into, and lastly is make a conclusion. So what is the network health assessment? Actually, to have a better understanding for this term, actually, we can compare the human patient health assessment with the network health assessment. For if you are a patient, you get sick, you have some symptoms, you can get a flu, and you want to go to the sick doctor. Doctor give you the diagnosis, use various different tools. They may take your blood and to file the blood report. So in the blood report, may actually list several parameters that is not in the normal condition. So based on this report, actually, you can help you. Doctor can help you actually eradicate this root cause, can give you the prescription. So that's the network health assessment. But unlike the human patient assessment, actually, network will not complain by itself. So it will rely on the user actually who use the network to get access service. They may file some complaints such as network speed slowly, and DNS connection is not good, and service quality is not very good. So the network actually, network provider and the management system will use various diagnostic tools and to try to dig into the network and try to identify the root cause and to recover the network failure as soon as possible. So that's our idea. The goal actually is to try to provide the network parameter and to build some application based on big data technologies. So what is the overall goal, overall objective for our network health assessment? We set several goals. First is network awareness, because currently the many networks are deployed, but the network has a slow response to the network change and network events. So what we like to do is increase the network awareness to actually have better response to the network events. Second is service assurance. We see a proliferation of the various services are proposed. Many services actually are sensitive to the packet loss, jitter, latency, and so service assurance became very important. And then for the metric definition calculation, what we really like to do actually is for network health assessment, we can define a metric to provide the network parameter to assess the network health. So this is a very challenging job because right now many metrics are proposed in different layers, network layer, application layer, but there's no single metric to measure the network health. It's a very challenging job. So for network optimization, what we really like to do is build the closed loop feedback to actually schedule the network resource to meet the customer needs, service requirements, and performance monitoring. And we see actually we need to trace the traffic over the network, but it consumes large amount of resources, server resources, network resources. So so performance monitoring is also very important. Last actually is trend analysis. This is critical because it will help you to actually correlate different events to anticipate the network change, and they will help you to predict the network failure, and you can recover the network failure as soon as possible. So what is the network health indicator? So we try to do this metric. It's a new metric we proposed to other SDO, and we want to compare with QoE metric and MOS metric. For many people familiar with the MOS score, and actually MOS score actually they can provide numerical indicator for human perceive of the service quality, and so for the network health indicator, actually they can provide the numeric indicator for the network impairment anomaly degree from the network impairment perspective, and so the common sense. Not only the MOS metric, but also the network health indicator, both can be used to increase the network awareness and help to provide better the service assurance. But the difference, they have a different data source. For MOS score, and you more rely on some application layer data, such as frame loss, GOP, and frame related parameters, and but for the network health indicator, we more rely on some like underlying network data source, like you can get data from the syslog, from the SMP, from the OM protocol, from gRPC, and whatever protocol you can use, and you can support online, offline data connection. And actually, the other difference, actually, the MOS metric more rely on the QoE metric or QoE model algorithm define the I2D cycle tail. For our metric, actually, we will use the big data technology, so such as network anomaly assessment. So this is the architecture we propose for the network health assessment. We have this architecture comprises 3 layers. In the underlying, we have a data providing layer. They will actually get the data from the network. They support the online and offline data connection mechanism. In the middle, we have data analytics layer. We can use the data in the data providing layer, and we can aggregate these data to do some filtering, and we can remove the duplicate data. We can add missing data with the average of the existing data, and we can do some analytics. And we build several capabilities such as network anomaly assessment, trade assessment, and root cause analysis. And in the top, we have various different applications. Actually, the top layer can use the capability in the middle layer. They can build a vast API. Using the API, they can build a different application. So one typical application we propose is the network health assessment. The other applications, such as the network benchmark application, you can actually do the network acceptance test on various different network. They can help you to do the better network planning. So this is several use cases we proposed. The typical use case is network innocence proving. This case actually is a typical we really want to drill down. And for example, for when the service quality is get down, sometimes it's caused by the network problem. Sometimes it's caused by the head-end issue or terminal issue. So if we have the network health assessment model, we actually can prove the network innocence, can prove this is not a network problem. Other use cases like network benchmarking and the trade analysis and network telemetry. We also have proposal in RTD Stack 12, and I don't want to go to the detail. You can check that. And for network telemetry, I think this is a critical part. Is actually they provide the data for the network analytics, and the data quality will decide the network diagnosis accuracy. So we actually, in our project, we use various different data sources, such as syslog data source. We can get the config data, log data, alarm data, and KPI data, performance memory related data. And we support online and offline data connection mechanism. And we can correlate this kind of data with the network topology. They can help you better to identify the location of the failure and occurring time of the network failure. In IETF, various different data connection mechanism they call the network telemetry protocol are proposed. Typical one actually is in-band OM and gRPC, and also they have data probing, and they share a lot of commonality. And one of the challenging issues is if you really want to pass the network telemetry data efficiently, you really require the hardware change. But I think it's worse. It's very promising. For the diagnostic and analytical system, actually, they will take input from various different data sources, such as syslog data source, and they will actually use this data and to identify the root cause. And this data actually can be used to generate different data objects. This data object can be used to perform the network anomaly assessment. The basic idea is to check the consistency issue between the different equipment. And sorry. Also, actually, this data object can be used as input to the rule engine, and the rule engine actually can be used to identify root cause. They can rely on some fault rules database, and this fault can be the rules can be performed, and we can actually, if there's any fault in the data object match the fault in the data object fault in the fault rules, actually we can trigger the root cause analysis, and we can support the British search first and widest search first. Which one is used will it depend on the policy we used. So for the capability we built, actually one typical one is anomaly analysis. We support the spatial domain analysis and time domain analysis. Spatial domain analysis actually tell you how the data in one equipment is different from the data in another equipment, especially from neighboring the equipment. So this will help you to check the consistent issue. So they will can do the anomaly analysis. And for time domain analysis, actually they will compare the past data in one equipment with the current data in the same network equipment. So they can do the consistent check from time domain perspective.
Sorry, Chin, we're going to have to go to the conclusion slide because
okay,
we're reading into other people's.
So for metric definition, I would be short actually. We cannot boil the whole ocean, so we need to actually portray the network with a lot of concentrate. So we establishes the profile for the different network to narrow down the network type. So we can give a lot of district. With this network profile, we can actually define the measure from different different perspective. Right now, we focus on actually anomaly analysis aspect, but we want to expand to look at some risk assessment and SL assessment. And so in this case, we can provide the network health from different domain. And so concluding, actually, as I discussed earlier, actually troubleshooting is very hard for many different reasons. And for network health indicator actually is very useful and for the network diagnosis, because it can help you to recover the network failure as soon as possible. And to achieve this, actually, network telemetry is a key for the network diagnosis or network analytics. We really hope the network telemetry protocol can be standardized in the IETF. In this case, we can have more efficient network analytics because we really want to have some not only offline data analysis, but also we have online data analysis. So they really depend on the network telemetry protocol that it be defined. That's all. Thank you.
Okay, fantastic. So we don't have any time for questions for Chin, unfortunately. So please take them to the list. Alex, fantastic. Thank you, Chin. So Alex, apologies, but I did email you. We have to reduce your presentation time. Thank you, sir.
This is not my conclusion, but I could use it. Fine. My name is Alex Gallis from University College London, and I would like to introduce to you a number of problems which could be solved, including easy deployability of SDN if you take into account another concept. That's the purpose of my presentation. Although with my colleagues from Huawei, Kiran, and Delay, we produced a document which was submitted to ANIMA working group, what I'm going to do in this presentation to provide to you the motivation for a broader applicability of the network slicing in IETF, and also to say that this is quite urgent. Now, I'll go through a bit of history, but also focus on the conclusion and future work. Now, network slices is probably used before, more than 10 years ago, in the active network research and test-based research. But at that stage, the concept was mainly about grouping physical resources, later moved towards grouping of logical resources, and later used to other things which are approaching now. Some other definitions are listed here. And currently, to my knowledge, all the big standard groups are looking into how to use this concept in a current mode, which is basically dictated by the fact that 5G research, which is backed by the operators in big way, are adopting this type of concept. And as a result, the networking infrastructure has to somehow support it. The issue is how well and what to do with it. So these are another definition which exists, coming from NGNM, but also some others. More recently, the IMT 2020 ITUT working groups also produce a definition of the network slicing and the way to handle it in a mobile network area. However, this concept is applicable mainly to the fixed line networking. Now, there are a number of key characteristics. By the way, this is my older slide. I produced some others, which makes this area a bit more usable.
although the original network slices were mainly a partitioning of resources, currently it's a dynamic system which could be put in place, allowing multiple deployability of different heterogeneous systems. Some with some characteristics, some with total different, and this is make it very convenient for the use in a networking or SDN. It could be used for different type of services. That's where the operators are extremely interested to use, mainly in the area of different services, using different quality of service or different management and operation capabilities or different optimization done in parallel. So for this is one thing which brings the things together. For example, in a case of SDN, it does not automatically assume that the whole infrastructure is SDN enabled, which is not going to be a case for a long time. Now, in order to bring together this definition, at least we proposed a unified means to move forward, which includes 4 dimensions for the use of slice networking. Obviously, there is a need to have a grouping of physical and logical resources and virtual resources. Very important is also to have a set of network functions, some of them virtualized or attached to that group of resources in a second dimension. The third dimension is a type of services and service components which could be characterized and put in place related to a slice. And very importantly, in my view, is the fact that this entity, which is a dynamically created on demand, potentially should be controllable through a set of characteristics which are offered by the slice. Not all the slice characteristics could be highlighted, but in some sense, this capability exposure is an element to control it and manage it properly, allowing interworking and multiple orchestration across a network. There are plenty of requirements in terms of why this concept could be put in place, and this is just a short list of them, but it's due to the fact that the current concept is targeted towards the usability in service related usability. It looks to me that this will be the norm rather than exception. Now, we applied it to autonomic infrastructure, and by inserting, if you want, additional elements related to the network slices, which are capability exposure and autonomic orchestration, in addition to the functions which are need to be looked at and resources. And this will be was provided into this initial document which I mentioned, applicable to Anima group. However, when it comes to SDN, there is a possibility to insert, if you want, this concept in the overall SDN architecture and take advantage of it, because clearly the network slicing is here to stay due to 5G and operations. So on one hand, it's an opportunity to take advantage of it. On the other hand, there are a lot of work to be done to make it usable. And this diagram shows that one example where this could be inserted. So potentially, SDN does not apply to the whole set of networks, but it could be applied to one part of it, which could be created on demand. Other parts could be dedicated to other type of heterogeneous infrastructure. For example, ICN type of services, which could sit in the same network, sharing the resources, but not necessarily colliding to each other. And this is quite an important aspect. There are plenty of work to be done in order to make this concept, if you want, applicable and usable, both in SDN as well as in other areas of internet. And this is just a shopping list, quite a long list, and it has to be put in place gradually. However, most of it will take advantage, hopefully, of this heterogeneity in terms of the deployability of a system in a current networking without changing the whole infrastructure. So my conclusion is listed here, namely I introduced this area and in particular to SDN work as a means to move forward from the existing bottleneck which exists in my view in terms of deployability of SDN, because most of them requires full SDN capability, which is not practical, will not be in place 10 years from now. So in the meantime, there is a possibility to shape, if you want, a bit the SDN architecture, if you can call it that, and take advantage of this opportunity. And I'm inviting everybody to allow this to contribute to it. It's just a beginning. Thank you.
Thank you, Alex. So there's going to be a side meeting tomorrow evening on network slicing. Is that correct?
Yes, there'll be a side meeting at the end of tomorrow's, I think at around 7 o'clock, where most of these topics will be put in place and maybe other presentations, but it will be an opportunity to discuss it further. However, in case of SDN, this is a particular aspect which is very near to my heart, and I would like to encourage this to move forward on this direction to take advantage of the capabilities of network slicing. Thank you.
Thank you, Alex.
Hello, everyone. I'm Daniele Ceccarelli from Ericsson. This is basically a report of an interoperability test that we did. Actually, we started some months ago. That will be that has been shown at the hackathon and will be available for let me say, a more interactive viewing at the next Bits and Bytes. What it is, what ACTN is? ACTN stands for Abstraction and Control of Traffic Engineering Networks. It's pretty much related with network slicing, again. It is considered as the SDN architecture and solution in IETF. It is a work that is being progressed in the TIS working group. It is based on a hierarchy of SDN controllers where 3 different types of SDN controllers are defined. The customer network controller, multi-domain service coordinator, and physical network controller. We will briefly see what we are speaking about in the next slides. The demo, the interoperability was shown with an MDSC from a vendor, speaking with different PNCs from different vendors. So the architecture, as we said, the CNC, the customer network controller, could be an application, could be an SDN controller, but it is something that is under the control of the customer, while the MDSC and the PNC are usually under the control of the operator. The PNC is the physical network controller, the thing that speaks directly with the nodes. The MDSC, it could be a controller, it could be a functionality inside a controller, which does coordination when it comes to traffic engineered paths in the network. This is the scenario that we used in our interoperability event. We used 2 IP/MPLS domains, 2 transport domains with emulated nodes, and we focused on the MPI. The MPI, as you can see here, is the interface between the MDSC and the PNC. Basically, the idea was to show the capability to provision end-to-end virtual networks in a multi-layer, multi-domain, and multi-protocol environment. These are the drafts that have been used as the basis for the event. Basically, we have 2 drafts in the TIS working group defining the requirements and the framework for ACTN. the applicability of existing young models and the PCEP extensions to ACTN. And when it comes to protocols, we have two different choices. It is possible to implement an ACTN hierarchy using PCEP. These are the two drafts that were used for the PCEP declination of the demo. And it is also possible to use young models. We use the RESTconf, for example, in our scenario, and we use it for topology and service provisioning. We have the full list of use cases here. We are running out of time, if I'm right. So please have a look at them if you are interested. You can contact any of the authors for any further question. Future work, the idea is to continue doing these interoperability tests. We have here a site where we are collecting all the different requirements, protocol extensions, interoperability tests tests that we are doing. So if you're interested, you can find a lot of info there. What else? That's it. Again, the demo will be available at the Bits and Bytes this Thursday.
Did you find an issue in the standard spec in this demo? No.
Not so many.
Not so many. Okay.
Thank you, Daniele. Okay, and Sarab, so our final presentation, SDN security trust models. So apologies, everyone. We're going to run over by about sort of 5 minutes.
Yes.
Yeah. Okay.
Hi, myself Saurabh Chattopadhyay, and I'm just going to give you a quick overview of the kind of work that we're doing in SDN security, trust models, architecture hardening. This is the work that we are carrying out in the SDN research group. One of the draft is the basis of this presentation. So just quickly revisiting the context, or rather the objectives or use cases that from where we started. So this is like SDN, two different SDN security domains, as you can see below. And you have this network sharing going on between the two domains. Each domain has their own private network. And the two domains are essentially supporting a lot of different business cases, use cases on identity sharing, function sharing, resource sharing. Now, when this is going on, when let's say the new requirement comes in for dynamically inserting a new domain altogether between these two existing domains, and then the situation for that dynamic insertion will typically introduces complexities in defining the network sharing, defining the integration of these domains altogether. And that is where, when you're trying to create the network from grounds up, new network, new interfaces, new policies, SDN comes in the picture. So this is where dynamic insertion is pretty much possible with, the kind of SDN capabilities that we have today in the infrastructure. However, the operational security policies are still, to a certain extent, limited in a manner that it doesn't give you enough resource sharing capabilities across different domains. It doesn't give you an on-demand trust establishment capabilities across domains. So that's precisely where this draft is focusing on. There are various business scenarios which are addressing these, these requirements. RFC 7832 is one of the published draft from AFFAB working group. It's defining some excellent use cases, and this draft is defining what is required for addressing the challenges. So today, if you look at the situation, when you're typically looking at the infrastructure, there are a bunch of challenges that people are heading on. So the resource sharing policies, they don't have provisions for validating the external domains. They don't have easy cross-certification options. There is hardly any automation underlying for PKI provisioning. So how people are trying to, work around those challenges, they're kind of, trying to build a self-certification layer in the applications. Now, the question is, the application is not knowing what is the underlying infrastructure that is going to get allocated to it because the underlying resource allocation is happening dynamically. But still, the attempt is being made to ensure that the self-certification at the application layer is vouching for the underlying ever-changing infrastructure as well. Then applications not relying on the attestation from underlying infrastructure. So let's say the application is self-certifying and it's trusted boot as well. It has booted up in a TXT, leveraging the TXT technologies, but then there is no way to let that communicate to the other party. So the other party who is leveraging the certificate which are self-certifying, it's not being able to distinguish between the trusted boot applications and non-trusted boot application. Then the RBAC policies that are getting defined today in typical OpenStack, if you consider OpenStack infrastructure, the Neutron Keystone agents are defining the RBAC policies, but then these are primarily getting defined through trusted external IPs or CIDR routes, which are vulnerable to IP spoofing. There are reverse proxy mechanism being in place, which is again, kind of diverting the traffic to the tenant. Basically, it is tenants are leveraging reverse proxy to hide the names, the resource, the original owners of resource. What was their names in the actual the actual infrastructure? They are bearing that name, and the tenant is trying to hide it by leveraging reverse proxies. But then essentially, there is no cross-certifying happening because of that. The multiple names cannot be. It's not getting considered today in the current situation. So these are challenges that we have seen, and what we have realized over the last more than a year when we are working towards addressing these challenges, that some of the work groups are already producing the kind of standards that can be leveraged. Like for example, AFFAB and scheme drafts are pretty much can be leveraged for creating the federation identity part. However, they don't provide options for dynamic pre-provisioning of underlying trust, but then the work happening in ACME draft is essentially covering that part as well. It's kind of giving a way to integrate an ACME implementation in the OpenStack infrastructure or SDN capable infrastructure. And then we see UNF is also coming up with the SDN hardening guidelines, which is essentially about hardening the SDN controller to SDN elements interfaces. Now, all of that is happening. However, we also see that the industry, the actual implementation is varying from what the standard bodies are perhaps suggesting. So it looks like for SDN, specifically for catering to the SDN requirements, there is no reference architecture, there is no guideline available, and that seems to be the way to go forward. If there is a reference architecture available, if there is a guideline available for laying out a PKI infrastructure, which will give an essential dynamic trust establishment capability to the SDN infrastructure, that's what I think, what we think is probably we need to get at. That's where, so the recommendation is to, consider the SDN research group to identify this as one of the area if it suits. Thank you.
Oh, wonderful. Thank you, Sarah. So apologies again for running over time, but actually SDN security is a really important area. And the last but one slide where you're talking about the ONF guidelines, I mean, these have come very late, right? Yeah. Sun just got Howard and Dechang and the ONF security working group still talking about sort of general sort of principles around securing the SDN network. I'd really like to see more of the SDN security requirements, the challenges being discussed in the working group, and definitely open to kind of having some documentation that kind of sits within the working group that then feeds other sort of protocol specific solutions. So cool, let's continue this on the list, I think.
Sure.
Maybe Diego will initiate a discussion on the mailing list.
Absolutely, I'll do that. Thank you very much.
Okay, thank you everybody. That's our Sdnrg concluded for today.
3 minutes over. Oh, yes.